Good morning, good afternoon, good evening, wherever you might be, and welcome to one of my more physicsy posts. It's called Quantized Gravitational Conflation. And if you've ever felt confused about what spin means on an intuitive level, I think this post is for you. Because in the classroom, you're often told that spin is kind of like angular momentum, but not really, and then there's this sort of vague hand-waving stuff that goes on. But I think that if you understand the geometry of surfaces and volumes, it becomes ridiculously simple. So first of all, if you're not properly introduced to the topic, spin-2 gravitons make no sense as fundamental particles because they seem to be composed of more fundamental subcomponents. For example, I can imagine fundamental concepts for a spin 1/2 and spin 1 particle because it is difficult to break them up into smaller components. When a volume gets trapped in a film or surface, it must spin around twice to conserve angular momentum. And this explains why a photon with, is that spin 1/2, is a swirling volume while an electron is a spinning surface, like a spinning bubble. And when they have the same amount of angular momentum, the bubble, or the fermion, or the electron, will spin around twice as fast as the volume, the boson or photon. In more intuitive terms, when a spinning bubble pops, the remaining volume will be spinning around at half of the rate of the bubble. Whatever a spin-2 particle is, a graviton, must be something that completes the following geometric sequence. The Higgs is nothingness and it has spin 0. The electron is like a bubble and it has spin 1/2. And the photon is like a volume, which is spin 1. Whereas a graviton has a shape more like a toroid or a tesseract, which is spin 2. And this toroid is nothing more than something with it's a volume with a hole in the middle, and that's spin 2. It's sort of composed of two different types of geometric objects, a surface and a volume. Clearly, such a toroidal shape would have to spin around by a quarter as much as a cube-shaped bubble would have to spin. For a tesseract would have to spin around by a quarter as much as a cube-shaped bubble would have to spin around to return to the original state. And there's a nice little GIF in the blog post linked below that helps you visualize this. In less abstract terms, a spin-2 particle is just a volume with a hole in the middle. I'm repeating myself, but sometimes that helps. Do these things actually exist in nature at the fundamental scale? I mean, is there a fundamental particle that is a donut? Or are people just trying to use these objects to show off or paper over things that they don't understand? When gravitons, these spin-2 particles, are translated from the language of spin into the language of dimensions, one certainly gets that sort of impression. For example, the spin-2 graviton can be thought of as something that exists in a fifth dimension, rather than just it's a donut. But what does a fifth dimension really mean in intuitive terms? An apple sitting on a table and doing nothing exists in 4 dimensions. X, Y, and Z stay constant, but t ticks away. If you pick up the apple and throw it, the 4 dimensions, x, y, z, and t, all change at the same time. However, one could also say that when the apple was thrown, it entered the 5th dimension, because it now possesses energy. The 5 dimensions of the apple are x, y, z, t, and e. But if you are a promoter of a fashionable theory of gravitons, like loop quantum gravity or spin foam, you might say that the apple on the table exists in 5 dimensions, even when you don't throw it, simply because the apple possesses the property of mass, and mass is the 5th dimension in their theory. But since mass is equivalent to energy times a constant, this isn't a major divergence from the simple example in the first that I just explained, with the apple being thrown. The energy of the 5th dimension refers to the stuff that is moving within the apple and or the motion of the apple relative to you. In this sense, saying 5 dimensions over and over like a magical incantation which opens the door to enlightenment is sort of like a parlor trick that physicists use to make themselves look more mysterious, interesting, and powerful than they really are. All that saying the apple exists in 5 dimensions really does is provide a trumped-up or shorthand way of saying the apple or the stuff inside of it is moving. I know that spin-2 particles have been used to win a Nobel Prize for explaining the quantum Hall effect in terms of a theory about bubble geometry, known as the Gauss-Bonnet Theorem. But those Nobel Prize winners didn't come out and directly relate that theory of a collective effect to gravity, and I wonder why, because the connection's somehow obvious. I think I will go ahead and do that. A deformed bubble interacts with its own oscillation in a predictable fashion, described by the Berry phase, something that is described with the quantum Hall effect. I'm just trying to provide some keywords in case you want to investigate this on your own. The deformations act like a drag that warps the surrounding space, giving rise to electric and magnetic fields. If one thinks of the initial driving oscillation that deforms the bubble as the cause of its ability to gravitationally attract other bubbles, then, since the Berry phase shift results from this oscillation, this is a way to mathematically describe how electromagnetism and gravity are linked. A driving gravitational oscillation with spin 2 gives rise to drag around a bubble surface with spin 1, which causes an electromagnetic oscillation of a volume with spin 1/2. If you can translate that into a mental image, I think you understand physics. If you can't, you don't understand physics, and you probably shouldn't become a physicist, because far too many people confront their inability to visualize something and then they go crazy and start trying to formalize things and express them in other languages, and the result is absolutely absurd. I think those people would be better off doing something else. So I'll say that again. A driving gravitational oscillation with spin 2, this is the donut, right, gives rise to drag around a bubble surface with spin 1, which causes an electromagnetic oscillation of a volume with spin 1/2. And I think this means that a graviton is merely a combination or conflation of a photon and an electron. And I think that this is similar to how a photon or an electron is a conflation of a particle and a wave in the classical sense. You know, a particle, it's a point, maybe defined by some sort of rotational motion, and a wave is linear and oscillatory. If this is the case, then a graviton is a composite object, and a composite object cannot be fundamental. It is a collective effect, and it is misdefined as being a fundamental particle. It may represent the photon-like energy radiated by bubbles oscillating in sync, and at the same time be a description of the energy exchanged between bubbles between a vibrating volume and a bubble composed of smaller bubbles. The concepts are two sides of the same coin, and if you start early enough with thinking visually, you will be able to create mental pictures of all of these things I've said in words. If you can't, you may end up trying to take the mathematical formalism and turn that into computer simulations which create these pictures for you. And I suppose that is what physics is about. It's about creating pictures so that we can transfer that the picture from one person's mind into another person's mind, and they both say, yes, we agree, we both have the same picture in our minds. There are easy ways to do that, just sketching a picture on a piece of paper, and there are difficult ways to do that, where you create a complex simulation and push run on a computer. I personally think that if you cannot create the image in your mind without the aid of a computer, you shouldn't be doing physics because you're missing an important skill. And that you will get confused and you should do something else, where you can, test your ideas in a more concrete fashion. Maybe I'm wrong. Probably I am. I'm saying this because about the graviton being a composite concept, because I don't like the trend that emerged after the World Wars, in which abstract concepts were conflated, and then they would take those conflations and conflate them again. We had conflations upon conflations upon conflations, and that is the state of modern physics today. I know that this is just a somewhat contorted way to express a recursive system, but I think that programmers can understand recursion perfectly well, and that we need to get rid of these opaque modern definitions and restore our language to a clearer, more grounded language in terms of the Laplacian and precession and, just simple unification of things. So, because I like the Laplacian, I'm going to conclude this post by talking about the Laplacian, because I think it's something that's worth understanding intuitively, just like spin. So here we go. The Laplacian is a differential operator given by the divergence of the gradient of a function on Euclidean space. That sounds a bit abstract, but the divergence of the gradient could also be written as the change of a rate of change, as in you are swinging back and forth on a swing and someone pushes or pulls on you. I have to tie math to a physical thing to understand what it means, and I have to have a mental picture of what it means. Otherwise, I don't think I understand it. And it took me a long time to realize that there are a lot of people who will write down all of the math, but they have no mental picture to go with it. And they can pass the tests, but I don't think they understand what they're doing, honestly. I mean, I just don't get it. How can you understand it without having a picture? So in the wiki on the Laplace operator, we read, it is named after the French mathematician Pierre-Simon de Laplace, 1749 through 1827, who first applied the operator to the study of celestial mechanics, where the operator gives a constant multiple of the mass density when it is applied to a given gravitational potential. Solutions of the equation delta F equals 0, now called Laplace's equation, are the so-called harmonic functions, and they represent the gravitational fields in free space. The Laplacian operator tells you what will happen to the mass density within a given gravitational potential energy well. If the arrows in the operator point out, the mass density decreases, and if they point in, the mass density increases. When the oscillating mass density is constant on average, you can predict the gravitational fields at a distance from the distribution as a sum over the harmonic functions. In other words, the mass density responsible for gravity can be described as a localized oscillation. Light can be described as a non-localized oscillation. With gravity, you have localized oscillations that radiate non-localized oscillations, which add up harmonically to create the gravitational potential energy well. And if you spend a moment, you can take this concept and go back to what I said at the very end about spin, and collective effects, and you can connect this concept from the Laplacian to what was said about spin. There's a fundamental connection that you have to think about a bit to make. One can consider harmonic functions which transform under irreducible representations of the conformal group or its subgroups, such as the group of rotations or translations. Proceeding in this fashion, one systematically obtains the solutions of the Laplace equation, which arise from separation of variables such as spherical harmonic solutions and Fourier series. In potential theory, you have things like Liouville's theorem about how the emittance of a distribution never gets smaller, and this can be connected to statistical theories like entropy. Once you connect all of these things together, you understand everything, more or less. I mean, that's how you construct a theory of everything. And people do this all the time in 50 different languages, their own private languages, but I think we should be doing this in the oldest language we know of, and I think that's why we should do this in the language of the Laplacian angular momentum. And, connect it to spin, but also tell everybody how stupid it is to have a concept that is such a conflation of a conflation. So, the Laplacian, the Lagrangian, and the Hamiltonian formalisms. This is something I wanted to understand when I was an undergraduate, but I didn't understand it until later. They can all be used to describe the same system, but the Hamiltonian is what everyone uses for modern physics because it keeps conjugate variables orthogonal, and it describes things in terms of momentum, whereas the Laplacian describes things in terms of velocity and mass density. The Laplacian seems like a more fluid description that motivates intuition about gravity in a really obvious way. But since the Hamiltonian formalism is typically used to describe quantum systems, as in you take yourself outside of the system and look at it from a distance instead of being in it, It's also used to describe anything with a relativistic process. The intuition behind the Laplacian has been buried in many subfields of physics, even within general relativity. This is somewhat ironic because Minkowski space comes of general relativity. It comes from generalizing the Laplacian to non-Euclidean space. But that is probably to be expected since the Laplacian is like a Fourier transform or inversion of Newtonian physics, and we don't have a Fourier transform of general relativity because it doesn't conserve energy. In simpler language, Laplace found the mass density of the potential at some point outside of the object, while Newton found the potential outside of the object given a certain mass density. Laplace saw that, as in Stokes' theorem, the gravitational potential outside of the sphere containing the mass is a harmonic function satisfying the Laplace equation, regardless of the distribution of the mass density. It was an inversion of Newton, just like the Fourier transform is an inversion of the time domain into the frequency domain. For gravity, the Laplacian operator represents the fundamental jiggle of our reference frame, which is the same jiggle behind everything from quantum mechanics to cosmic microwave background radiation. For electricity, it shows how a smoothly changing external field from a light wave gives rise to discrete concentrated flows of current and matter. More generally, when you have a Laplacian matrix instead of just a Laplacian operator, you are using smooth global properties at a distance to calculate the discrete concentrated local properties of multiple objects instead of just one. It is related to the problem of renormalization and the philosophical implications of boundary conditions. Whereas a photon is a quantized amount of radiation from a bubble-like electric charge that breathes or oscillates within a jiggling volume, the graviton is a quantized amount of radiation from a bubble-like collection of charged particles that breathe and oscillate within a jiggling volume. This is this recursion. Geometrically, they are both defined by a bubble-like surface interacting with a volume, and that combination of a spin 1 and spin 1/2 object is described by a spin 2 object. It is a lot like how a laser works, except that it is a laser shaped like a sphere that radiates short wavelengths in all directions that add up to create very long wavelengths, or like a toroid. It takes some time to develop the geometric models. If one thinks of a graviton as a quantized gravitational force mediator, which could be incorporated into the standard model in the same way that photons are treated as electrostatic force mediators, then it will necessarily be too small to be detected by any of the methods at our disposal in the near or distant future. Photon detectors are of the scale of electrons, and graviton detectors would need to be of the scale of planets. Instead of holding on to the idea of an unmeasurable particle called a graviton, we could throw this quantum graviton in the trash and reclaim the word by redefining it with a straightforward analogy from Heaviside's gravito-electromagnetism. Electrons repel, magnets attract and repel. Electromagnetic waves make atoms stable. Likewise, mass attracts, gravitons repel and attract. Gravitational waves make orbits stable. Gravitational moments are classical descriptions of the change in angular momentum of a non-uniform distribution of mass in a solid object, which is under the influence of a gravitational field. They describe the precession of a rotating, revolving object. One can define a graviton in relation to the gravitational moment in the same way that a magnet is related to the magnetic moment. In this picture, a magnet is caused by a current of charge and a graviton is caused by a current of mass. In quantum systems, we can connect the magnetic moment to the angular momentum, a quantity which depends on gravitational moment. Electromagnetic moment is the rate of change of angular momentum experienced by an electron in a magnetic field. It is given by the Bohr magneton, a constant derived from the relativistic mechanics of the Dirac equation. The gyromagnetic ratio between the magnetic moment and the angular momentum is twice what one would expect for a classical spherical volume of charge, but it is equal to what one would expect for a classical spherical surface of charge. By making an analogy with planetary systems, one might interpret the square root of the gravitational constant divided by the speed of light as a sort of conversion factor between the gyromagnetic ratios of bubble-like surfaces and volumes. It has been known for a long time, particularly from the work of Schuster Sutherland H.A. Wilson, though lately little regarded, that the magnetic moment P and the angular momentum U of the Earth and the Sun are nearly proportional, and that the constant of proportionality is nearly the square root of the gravitational constant G divided by the velocity of light c. We can write, in fact, where P is a constant of the order of unity. Back in the 1940s, scientists like Patrick Blackett believed that there was a relationship between angular momentum and magnetic moment, an extension of Maxwell's laws to gravitation. But later in his career, after witnessing the horror of the world wars and the atomic bomb, he concluded, based on experiments with magnetometers, that there was no relationship. He subsequently won a Nobel Prize for his work on the cosmic rays from outer space, which are akin to the particles emitted from an atomic bomb blast. I think that Blackett didn't get enough statistics in his experiments, and that he was on the right track early in his career with the simple equation relating angular momentum and magnetic moment. The idea that there is a simple analogy, gravitational electromagnetism, to be made for Maxwell's equations and gravity just went out of fashion, and I'm trying to figure out why. I think it was caused by a switch from Cartesian space to Riemannian space. In short, I blame Einstein and relativity. But I think that post-war politics and million-dollar Nobel Prizes played a role as well. It is widely believed that Blackett did a laboratory test which ruled out his equation. However, his experimental paper described a static test in which a 15-kilogram gold cylinder was placed at rest and presumed to pick up an induced current, producing a small but measurable magnetic field from the rotation of the Earth. In the paper I got that little bit of trivia from, the author S.P. Sirag goes on to describe measurements in astronomy which support the equation and suggests that the measurement be redone with squid magnetometers. Honestly, 15 kilograms of gold back in the 1970s sounds like a good way to embezzle some serious scientific funding. And if you consider the angular momentum of a planet being like an expectation value, it would match up quite well with quantum treatments. Some people are still researching how planetary mass and magnetic moment are correlated, and it might lend some support to bringing back Blackett's moment, if only as an expectation value in a quantum system. And I hope that this video has been somewhat soothing. Perhaps it lulled you to sleep. Perhaps you're trying to absorb these concepts in a more passive way as you go through your physics education. You can think of this video as a sort of scientific ASMR, and maybe I have convinced you of some of these things, and maybe I've just given you new language to express concepts that you're struggling with. In any case, I wish you the best of luck, and I encourage you to take a look at my novels. They are about scientists, and I think they're a lot of fun. Thank you for watching. Until next time.